Calculus! This is AP Calculus lesson 3-3! Graphical analysis, relative extrema, minimum, and maximum. So, relative extrema, that is another way of saying min and max. Relative extrema is kind of this broad umbrella category that just says you have a minimum or you have a maximum. So, I wanted to write out function relative extrema and then have you shorten it for me, but it turns out that it did not fit in here. Even if the logo wasn't there, it would not fit in there. But here's the definition. I already gave you the red star, which is not color printed, so it's a black star for you. But this is a red star. It is something that you need to have on the tip of your tongue for the rest of the year. If I say f relative extrema, you tell me f prime sign change. F prime sign change. Let's back up and think about what that means for a sec. F prime sign change. So on a graph of f prime is the derivative, so the derivative is changing the sign. It's a positive slope, and then all of a sudden it changes to a negative slope. On a graph of f prime, and we'll be seeing this in a sec, but just be thinking about this ahead of time, on the graph of f prime, that just means the height went from a negative to a positive. It went through the x-axis. If it went through it, then it is an f prime sign change. It is a f relative extrema. But if it just touches it, for example, if it comes down, touches 0, but then doesn't go to the other side, it is not an f prime sign change, but it is a what?
Function critical point.
Critical value, exactly. All right. Function relative minimum, f min. The definition is f prime changes. F prime goes from a negative to a positive. F prime changes from a negative to a positive. Think about what that means for a sec. If it went from a negative to a positive, what is that going to look like on a graph? I have a slope that was negative and then it is a positive. Does that mean it's a minimum? Oh yeah, I can see how that's a minimum. Let's see. And then we'll.
It'd be like a U.
Yeah, exactly. It's like a U, a smiley face. And then F max. Who wants to do this one for us? Just shout it out. Yeah, it's F prime positive negative. And you might be thinking it doesn't matter. Everything we've done right now is F prime. But once we hit, is it tomorrow? Yes, once we hit tomorrow on 3-4, we're going to be talking about F double prime all of a sudden. So you do need to distinguish between whether or not you're talking about F prime or f double prime. Eventually we're going to be doing these things called the f prime test or the first derivative test and second derivative test. All of these things are tools that go in the first derivative test, the f prime test. Let me add the negative here too. All right, so let's look at what that looks like on the graph. So let's look at this point right here. What is f prime? F prime is positive, negative, 0. It's positive because the slope here, and I should change my color because I'm talking about f prime. My slope here is positive because the line has a positive slope. All right, what about right here? What is f prime? 0. Yep, it is equal to 0, and of course we can see that just because we have a flat line here. Let me move this up. And then over here we have just any point over here. We have f prime arrow is, it is negative. Yeah, the slope is negative. It comes down like this. Let me get the slope correct and then I'll move it. Yeah, what that means is it was positive and then it's negative, therefore it's a sign change. The sign change will happen at a CV. So the sign change was here, which means that guy right here is, in terms of our notes, we know it's a CV, but a critical value, but we also know it's a something from up here.
It's a relative maximum.
It is a relative maximum, yep. Relative max. And it's also a what? What do you mean by negative?
Because when there's a relative maximum, that's when it turns positive to negative.
So yeah, it changed from positive to negative, I agree, and that's kind of embedded in the fact that it's a relative max, but what is the other word from these 3 stars that we can say?
F prime.
It's this guy right here, right?
What is that again?
The relative extrema. I put it on the left-hand side, relative extrema. So it's also a relative extrema. So this word relative right here.
Wait, does that refer to minimum and maximum on both extrema?
So relative extrema is both min or max. It's an umbrella word for minimum or maximum. More specifically, it is a maximum. If it's a maximum, therefore it is a relative extrema. Relative just means within a certain boundary. So within this boundary between here and here, the relative maximum is this point. But for the entire function, the relative maximum is infinity, because like if I include from here to here, well, now I have an even higher height. Relative just means you're restricted to some boundary. All right. And where is the other relative extrema? Describe it on the graph.
Where f prime equals 0 on.
Yeah, that one.
Yeah.
Yeah, so f prime is equal to 0, therefore it's a critical value, and it's also a, say it again,
Relative extrema.
relative extrema. And what type of relative extrema is it?
Minimum.
Yeah, it's an f min. I guess I should have said f max over here because that would be the correct notation, but it is a relative max. This is a function relative min. That's what this stands for. And that's because we had a negative slope over here. This was a negative, and then all of a sudden it turned into a positive slope over here. This is a positive slope right there. Between the negative and the positive, you have to have a relative extrema, unless you have something where you have a DNE, I guess. And even if it's still a DNA, it would still be a relative extrema because you'll still change signs. All right, now we're going to look at a graph of f prime. So this was a graph of f. This is f prime. It's in red now. So it's the same exact definition. Now, where do they occur? Now, where do I have a relative extrema?
Anytime f prime equals 0.
Not exactly. So think about this right here. If I come down and just touch it, that's not a relative extrema, even though it is equal to 0.
The sign changes. If anytime it passes through.
Anytime it passes through, exactly. It passes through what?
Y equals 0.
Yeah, passes through y equals 0, or the x-axis, commonly known. Yeah, so that's a relative extrema. So we'll say f relative extrema right there, because it passed through the x-axis. The height here represents what? Is it f, f prime, f double prime? What is the height of this graph? Height of the graph is f prime. Height is always whatever it's lifted there. Height over here must be, shout it out, f, yeah. So the height here is f prime, and we're looking for an f prime sign change. The height was positive here, so let's just put a positive height here. And it's a negative height down here. Because of this height change from a positive to a negative, it went positive to a negative. What type of relative extrema are we? That's a maximum, yep. So f max. By the way, just like the previous notes, this graph of f, I took the derivative with Desmos. This is what the derivative of this graph looks like.
It's kind of weird to see it as if it's like f of maximum.
Yeah, it is, right? It's passing through here. Like, it makes sense on the graph of f. It's the highest point. But when you're looking at a graph of f prime, it looks way different. All right, and where's the other relative extrema?
Where y equals 0 again on the positive x-axis.
Yep, and then we'll give it to arrow. What type of relative extrema is it?
It's a minimum. Wait. Yeah, it's a minimum because from the left, the function is going from
A
negative to positive.
Exactly. Well said. Yeah, it's going from a negative to a positive from the left.
So it's basically where the line is going through. So like for the one with the maximum, the line is going from all the way from the positive y to the negative y.
Yeah, exactly. Cool, cool. So I want to label this graph a little bit better. So we'll call this point, this x-coordinate A. This x-coordinate A, we'll call this x-coordinate B. This x-coordinate we'll also call A. This x-coordinate we'll also call B. So the relative extrema for both graphs are what then? Where x is equal to x equals A, x equals B. You could have just done x equals A comma B. That would have been fine.
U, like or symbol.
Union.
Like that. Yeah, it's fine to just list them this way too, because you're not doing intervals here. When you're doing intervals, that's when you want to be careful with interval notation. Because technically both of these are answers, but you don't want to do the intersection of them. I guess mathematically an OR would work here, but I think it's just fine to list them like this. And then the F minimum is at which x values? X equals B, and then therefore X max is X equals A. There they are. Nice. Don't know what's going on. All right, so our procedure. We need to look for F primes. Equal to what? When we're trying to find relative extrema, what are we setting F prime equal to? What are we looking for? Where F prime is equal to
0.
0. Yep. We're looking for the CVs first, those critical values first. So, if the sign changes, so if sign change, that implies that it's a relative extremum.
What do you mean by change?
So if the sign changes from a positive to a negative, so the sign is the positive or negative of it, and if that positive switches to a negative, or the negative switches to a positive, the sign has changed, then it goes to it means it's a relative extremum. And therefore you need to figure out if it's a min or a max, so that's step 3, and the trick, again, you've already seen this before, this is just in the procedure form. If F prime goes from a positive to a negative, it is a what? Is it it is a maximum. We'll circle it. We'll do a line here to divide it. If F prime changes from a negative to a positive, it is a minimum. The best way that I've remembered this is look at the first value, positive. I always associate positive with being max. Look at the first value over here. The value was negative. Negative I associate with minimum. Look at the first value. And that's all we have. Oh, we have a backside. Finally a backside. And this is adding on because last year's class had a little bit of trouble with how graphs changed. So first of all, get associated with what an even degree polynomial looks like. Even degree polynomials always have end behavior where they go towards the same value. So this end behavior, they're both going positive. This end behavior, they're both going negative. This end behavior, they're both going negative.
Oh, I see.
This end behavior, they're both going positive. So with a positive leading coefficient, an even degree polynomial will always point up with both sides. The left and the right end behavior always point towards positive if it's positive. If it's positive. Let me do orange because you can see that better. With even degree polynomials, both ends will point down for negative. And then with odd degree polynomials, my wife's class, they always do a dance. They go like this and this for odd. They do even that's negative. I don't think we need to do the dance in here necessarily unless we feel like moving around. But yeah, odd will always have one end go towards negative infinity, one end go to positive infinity. It will always be opposites. Positives will come from negative infinity, so it starts over here. The bottom left will go towards infinity, negative infinity, and the top right will go to positive infinity. It doesn't matter the degree. It could be a degree 9 polynomial, but the end behavior will still be the same as long as that leading term, the leading coefficient, is positive. And then if it's negative, it's the reverse. So now it starts going from the left-hand side, it starts from going to positive infinity and then goes to negative infinity. And again, it doesn't matter the leading, or it doesn't matter what degree it is. For example, this is probably a degree 5 polynomial. This is a degree 3 polynomial. It doesn't matter the degree. You can have a bunch of waves, but the end behavior, where it goes off to negative infinity and positive infinity in the x direction, that end behavior will go towards positive infinity or negative infinity in the y direction the same way. All right. So now that we know the difference between even and odd in terms of positive and negative, and before I even talk about that, I just want to talk about how I remember the difference between positive and negative, because I know they go opposite, but positive, if I draw the average line between positive, it's a positive slope. If I draw the average line, it should be a positive slope. If I do the average line for a negative quadratic, or not negative quadratic, negative odd degree, it should make a negative slope. For a negative leading coefficient, it's a negative slope. Negative leading coefficient, it's a negative slope. That's my trick for remembering it. You don't have to use it. You can just remember those graphs. But the important thing is every time you take the derivative, you lose a curve. You lose a, what's the best way of saying this? Curve is what I used last year. I'm just going to say curve again. Every time you take the derivative, you change directions one less time. So you're writing that, but I want to show you a visual example of why that's the case. I'm going to do it.
Like you lose one relative extrema.
You lose. It might not necessarily be a relative extrema, depending on the graph, but you definitely lose the number of times that it can change. So this one changed. So it went up. It changed once, twice, thrice. So this is a degree 4 polynomial. I always add 1 on to the number of times it changes. So 1, 2, 3. This was a degree 4 polynomial. This one, it changed once, so it's a degree 2. This one changed, well, I guess that's a bad example because there's not really a relative extrema, but it changes once and twice, so this is a degree 3. This changed once, twice, 3, 4 times, so this is a degree 5. And that makes sense because if it's degree 5, that means you're x to the power of, not 5, 4, x to the power of 5. When I take the derivative of this, it turns into 5x to the power of 4. Now it's to the power of 4. Now I've lost one curve. I'm going to this graph. And I can even show you with Desmos to do a little bit more of a simplified version. Desmos. Start graphing. I want my mouse back. If I have f of x is equal to something like crazy x minus 1 to the power of 5 or something like that, and I zoom, that's probably a bad example. Let's do x to the power of 1, x minus 3, x plus 2, or x plus 3 I guess, x plus 10, and let's put an a out here so I can actually make this thing visible. Okay, hold on. 0 to 0.5. Make this bigger. All right, so how many times does this change direction? Count them. How many times is it?
It's like 3.
3, is that what you got, Arrow?
Either 2 or 3. There's a mystery line in the corner.
So
3.
1, 2, and then 3, right? Is that what you got, Rochelle? So 3 times. If I take the derivative, f prime of x, and I turn this one off, how many times does this change direction? 2. When I turn that off and I do f double prime of x, just once. If I turn that off and I look at f triple prime, we're talking about jerks now, it's just a line. And if I do f 4 prime, it's just a number.
It's just a point.
Oh, well, it's a flat line, so I should say y equals that. It's just a flat line. And then if I do it another time, y equals f 1, 2, 3, 4, 5 times of x, it goes to the 0 axis, and it stays there forever. So this is what the transformation of these functions looks like. You have more changes, and then every time I take a derivative, you lose one.
So it's like getting a string, and like it's going from different directions. Once you go straight, it's basically like going from each prime, right?
Once it goes, you're kind of like straightening out a string. You're taking out a curve by pulling it and making it less curvy, right? So it went from this to this to this to this to this to this. And I guess both of these are technically constant functions. This is just equal to a number, 1.44, and this is just equal to 0, which is still a constant. All right. I just really want to drive home the idea of when you take a derivative, you change directions one less time. Because in the future, I'm going to be asking you of what's the derivative of a positive cubic? And you'll answer, it's a positive quadratic. Or what's the derivative of a 5th degree polynomial that's negative? It's a fourth degree polynomial that's negative. The negative sign doesn't go away. The positive sign stays there if it was there, but you're just going down a power. You're changing a direction one less time. We're okay? Give me a thumbs up. We all understand we're okay? All right, that concludes the notes. Go ahead and write your summaries now.